All right. So you can interrupt anytime if you want to ask a question. Um, and there's no stupid questions. And if you're not asking a question, if you could please mute your microphone. So these are the topics that we will be going over.
We can send this out as like an email to all of you guys, or ask the TA to post it under CCLE.
Yeah.
Yeah. All right. Yeah. So first things first, we'll talk about the lattice structure. So the lattice structure is essentially the base structure that the atoms form in an element. And as you can notice, you um, you have like many different shapes for the lattice structures. And one of the basic shapes is the cubic lattice structure. And you you can measure these lattice points or these lattice structures via the lattice constants, which is essentially the distance from one atom to the next. And Cody.
Oh yeah.
Yeah.
Also, for the zinc blende structure, so you basically have a cubic, a full body cubic, and then what you do is you take like A over 4, like from each I guess like point in the in like the lattice structure, you add like an extra atom there, um, and yeah, that's what makes zinc blende structure. It's what makes silicon crystals and gallium arsenide the way they are. And then primitive unit cell is basically the unit cell where you can like copy and paste it a bunch of times and make a crystal. So
Yeah.
yeah.
So like if you're trying to find the surface density of a unit cell, you for example, if we look at the zinc blende structure here at the bottom, you would find out how much of the atom is actually inside that structure. So if you like notice the four corners, there's only like an eighth of that of that sphere actually inside the unit cell. And then so you would add like an eighth from each of these ar- arsenic atoms, and then these on the each of the surfaces, each of the six surfaces, half of that arsenic atom is actually inside the cell. So then you would add 6 times 1/2 times the density or the atomic mass of arsenic, and then you would add the 4 gallium atoms inside there.
Mm-hmm.
All right. Yeah. So there are there are different impurities that can occur inside these lattice structures. So there are 4 main ones that people talk about. The vacancy, which is when Cody, if you actually want to, oh yeah, if you notice like if an atom is missing from the lattice structure.
Can you
So
turn off
like
the AC?
What?
what was that? Oh yeah. So like let's say like there's an atom missing from a corner of like a unit cell, or like missing from the lattice structure, like uh that's an impurity. There's an interstitial defect where there's an extra atom that essentially causes the lattice structure to change shape because of the electromagnetic forces happening inside it that repel the nearby atoms. And then you have impurities where there's a different atom inside your element. So, and you can have a substitutional impurity where a different atom takes the place of your original atom. Like let's say like you have like a silicon atom, and then you have a phosphorus atom taking the place in the lattice structure instead of the silicon atom. And then you have the interstitial impurity, which is similar to an interstitial defect, but instead of an extra element atom, you have like a different atom. Any questions? All right. Want to go to the next one, Cody?
All right, sounds good. So I guess quick question. So if you guys want to just answer in the chat, what are the primitive unit cells of A, B, and C shown below? Oh, I guess the answers are there. Or actually no, the answer is not there, but yeah. Guess I'll give you guys about a minute and a half to think about that. If you guys have any questions, just ask.
Oh yeah, sure. So the lattice structure is essentially like the whole element. So like a primitive unit cell, as you can see here, like it's made up of, it's like the base unit that you can use to replicate an entire lattice structure. So a lattice structure is made up of a bunch of primitive unit cells, if that makes any sense. Kind of like Minecraft, where you like have a bunch of you have like one block, and that's your unit cell, and then you replicate that to build something bigger, which is the lattice structure. Anyone have an answer?
All right. Well, basically the first units. Oh, sorry. The first one, for A, is just Can you guys see my pointer? Type type yes in the chat if you can see my pointer. Okay. Um, basically you have like if you think of like XYZ like coordinate system, right? Like you have the x-axis, the y-axis, and the z-axis. Sorry about that. I think I Yep. Sorry, I think I cut out. Anyway, uh so for the first one, this basically is your primitive unit cell. For the second one, it's basically the same thing as A for B. And then for C, you can actually form the same primitive unit cell as A, which is actually kind of funny.
The reason for that being that they're all cubic shaped unit cells. So because of that, you can make similar patterns. It's 8 dots.
Is the unit cell like a square of 4 dots?
No, it's actually the cube, the entire cube.
Oh, the cube is.
Yeah.
For B and C, do we not have to include the center, like the center atom as well? And then for C, do we not have to include any of the white ones? So they're all going to be the same primitive unit cell?
That's a good question. The interesting thing is, so basically, if you can think of, if we have like like four or not four, eight like of B's arranged in a cube structure, I guess, you can fit like 8 of A, and then in the middle of the 8 like A's, I guess, that you place in the middle, like another A, and that takes care of the center atom. And then for C, you do something kind of similar. So basically, you can place like, so like right here, that can correspond to here, and then you can like place another square here, and then yeah, so
It's
C.
if you, Cody, do you want to go back to the zinc blende structure? Actually, I think it's kind of hard to visualize here, but actually, if you like see, if you look at the purple dots, you can, or sorry, not the purple dots, the dots that are like in the face plane, you can actually see that they kind of create their own square. And so let's say you put like another unit cell nearby it, those face points can actually create another cube that's essentially independent of your other unit cell. It's kind of like a diagonal. Yeah, the zinc blende structure is the purple one, but it's like essentially a diagonal cube, if that makes any sense. There would be like two different uh shapes going around, but still only one unit cell.
Did we answer your question? All right.
Oh, yeah.
Okay.
All right. Yeah. So some like basic quantum mechanics stuff. So like all energy in quantum mechanics or like in particles are quantized, which means that they have like discrete energy levels. So and that's calculated with the energy is equal to the Planck constant times frequency of the particle. Yeah, and then momentum is related to the Planck constant over the wavelength. And the photoelectric effect essentially says that all like materials can absorb a certain amount of energy, but if you have a particle that essentially surpasses that energy limit, it'll emit a particle that's equal to the difference of energy. So yeah, as you can see in the diagram, if you put in a particle or a wave packet that has 2.25 eV and your surface absorbs 2 eV, then you get out a particle that has 0.5 eV. And then you can use the equation to calculate the frequency of that particle as well as the speed.
Mm-hmm. Also, a couple interesting things to note. You can also use h bar times omega for your energy equation, where omega is equal to 2 pi f, and h bar is just Planck's constant divided by 2 pi. And similarly for momentum, you can use h bar times k, where k is the wave number, and it's equal to 2 pi over lambda. And the momentum equation, it's also known as the wave-particle duality, meaning that like everything is, both like a particle and a wave kind of. And it kind of stems from both the uncertainty principle and the momentum h over lambda. And yeah, and also light is both a particle and a wave. There's particle wave duality. And that's from both the Young's double slit, and that suggests that light's a wave, and the photoelectric effect, which suggests that light is a particle. So are there any questions about this?
Yeah, the essential thing to get from quantum mechanics is that particles can be expressed as waves and vice versa. And we'll see some examples of that in some later slides.
So first we have a quick problem. So do you guys think it'd be a good idea to split into breakout rooms, or do you guys want to stay here and just work on it yourself for a couple of minutes? Okay.
All right, yeah, we'll give you guys a couple minutes to work this problem out.
Also, you can put it in like meters per second if you want. There's no need to convert. If you guys are done with the problem, just raise your hand, I guess. To let us know.
Or type it out in the chat. All right, we'll give you guys one more minute.
Why is it minimum instead of maximum? So technically, maximum certainty is infinite. So the key idea in this problem is just that we know that momentum is equal to m times v. And then we know from Heisenberg's uncertainty principle over here that delta x times delta p has to be greater than or equal to h bar over 2. So meaning that we can pull the m out. So we get delta x times delta v times m is greater than or equal to h bar over 2. So if we know, if the uncertainty in position is 0, then the uncertainty in momentum must be infinite. So it's not a meaningful problem to find maximum uncertainty. I hope that answers your question. But looks like a good amount of you have also completed the problem. So this is in miles per hour. In meters per second, it is, yeah, you guys are correct. 3.515 times 10 to the negative 36 meters per second.
All right, Cody, you want to take this one?
Yes, I will take this one. All right. So there's an all-important equation in quantum mechanics called the Schrodinger equation. Could I show 7 again? Oh, yes. Yeah.
Yeah, h bar is a constant. Sometimes it's just easier to represent it with the, yeah, by h over 2 pi, because sometimes the equations work out better.
Yeah. H over 2 pi pops up a lot in quantum mechanics. And so a lot of physicists just write h bar. It just shortens equations. Do you guys have any other questions about this solution that that you need me to go over?
Yeah, or about anything we've talked about previously. We can go back to these at the end of the slideshow as well.
Oh, so yeah. So why is it 2 times delta x? So basically, if you remember from if you remember from the uncertainty principle, you have delta x times delta p greater than or equal to h bar over 2. So so if you start with delta x times delta p greater than or equal to h bar over 2, then you move the x over. So that's where the 2 comes from. It just comes from the original equation. Yep. All right. I guess we can move on. So Schrodinger's equation. So it's basically the all-important equation in quantum mechanics. Basically because there's this wave-particle duality, and there's this uncertainty principle. You can only know things like with a certain degree of probability, and so that's what this wave function tries to get at, right? It tries to capture the wave nature of reality while also capturing the probabilistic nature of quantum mechanics. So basically you start off with the time-dependent Schrodinger equation, right? Where you have position and time. And basically what you can do is there's this trick, right? You can say, oh, I have a function that depends on both position and time. Well, that function, I can also express it in a way where it's the product of a single function that's only the function of position times another function that only depends on time. And then once we do this, we can do some differential equations to get the time-independent Schrodinger equation. The exact derivation is also in Neamen, and you probably will not be asked to do this derivation on the exam, so we don't feel necessary to go over it. But this is the approach that you would take if you were to do it. And then, one sec, I have to admit someone. All right. And then Born's rule. Basically, this is what allows the Schrodinger equation to capture the probabilistic nature of reality, being that if you take the wave function and you square it, so basically wave function is a complex function, meaning that when you square it, you take the wave function and you multiply it by its complex conjugate. And that's the wave function squared. And that is the probability per unit length of the position of the object. So basically you can integrate over the entire region. You integrate over all space is 1 because the particle or wave is somewhere in space, right? And you can integrate over a certain region to get the probability that the object is within that certain region. And then also for the boundary conditions, we have the conditions that the wave function must be finite, single valued, and continuous. What that means is that the wave function cannot be infinite anywhere, so it can't like blow up. It has to be single valued, so meaning that if you take some like position x, right, it can't have both a probability of 25% and a 50% chance of being there, right? That doesn't make any sense. And it has to be continuous. And also the derivative has to be finite, single valued, and continuous as well, wherever a particle can exist. For the 3D Schrodinger equation, if you're ever asked to like write it down for whatever reason, because it's Chile long, you basically what you do is you replace the second derivative of x squared, and you replace it with something called the Laplacian operator. I believe most of you have seen it before in multivariable calculus. Yeah, are there any questions? All right, moving on.
All right, yes. So building off the idea of boundary conditions and the Schrodinger equation, you can model these unit cells by having something called a potential well, or you can model these like particles as like being stuck in a sort of potential well where it exists in an area where its potential energy is 0 and it can move freely, but then as soon as it like hits one side or the other, it encounters a sort of potential wall where its potential energy is infinite. It's unable to cross into that region. So because of that, or it like kind of approaches a standstill, and so you can assume that in it it's a standing wave. And the general equation for a standing wave in is like one wave equation going one way, hence the a1 e to the positive kx, as well as another wave coming back, which is the b1 e to the negative kx. So, and those they'll interfere with each other to create your standing wave. And as Cody mentioned in the previous slide, these wave equations have to have boundary conditions. So in this case, you know that there's no activity happening in the infinite potential areas, so there's no particle there at all. So there's no movement at all, which means that the position is 0, and then the boundary condition essentially states that what happens on one side of the boundary has to be happening at the other side of the boundary. So if one side is 0, then the other side is 0. And you can actually see that if you look at the figure, where at the two ends of the nodes, down in a figure B, the waves actually meet up at that 0 point at the energy levels. And then when you try to solve for where the function is spatially, you do take the normalization condition, which is what Cody mentioned earlier about multiplying the wave function by a complex conjugate or squaring it to essentially get a graph that has an area of 1. And when you get that, these are the equations that you get for to find the position of a particle in a box or in a well. Any questions? Oh, you can also see that like the energy is quantized as well, but it's not like linear. Like the difference between N1 and N2 is smaller than the difference between N2 and N3. and so on and so forth.
Yep. And this non-linearity and the discretization of energy is also later on when we talk about like density of states is what also like causes the density of states function to be like quadratic. And also for the potential well for the waves, you can kind of see that it kind of looks like standing waves, as you would see like if you had to have like a pipe and you were to play like sound through it. You'd have like, you know, the first fundamental, and then you have the first harmonic, the second harmonic, and so on and so forth, right? I think it's very cool how you can see these different parts of like physics and engineering come together.
Yeah, so the NE, it's basically like when you're essentially taking in order to arrive at these solutions, you're taking the general equation, the general solution, and solving for the boundary conditions, which is that here, like one side's equal to 0, and then the other side's equal to 0. So this wave equation has to be equal to 0 at both x equals 0 and x equals a, which are the two ends of the well. And then when you work out, yeah.
So the boundary x less than 0 should be 0 to a, with the potential in the Schrodinger's 0. Yes. So in region 2, the potential is 0. And then in the boundary x less than 0, so in region 1 and 3, the particle does not exist there.
Yeah, so it has the infinite potential.
Yeah, and then region 2, there is no potential. So that's why the K1 is square root of 2me over h bar squared. And there is no potential term.
And going back to the even odd question, once you like solve for the boundary conditions, you get like a question with like a complex wave function, but then when you plug in 1 and 2 and 3, they cancel out such that you end up with just a sine and just a cosine for even or odd, respectively. Does that answer your question? Yeah, so like once again, they're like the way they're arriving at these last equations is they're taking this general solution and then they're normalizing it, which is essentially taking the probability density of it. And since you know that it's equal to 1 and you know the boundary conditions, you can solve for these equations down here.
Yeah. Oh, yeah. And then this over here, general solution, it should be from 0 to a.
Oh, yeah.
So the hydrogen atom. Yeah, I saw on you guys on Shiwei's midterm last year that there's a question about the hydrogen atom. So yeah, so basically the actual math to derive the actual equation is kind of too hard. I looked into it. It's pretty scary. So basically, you take the radial 3D Schrodinger equation, you solve by separation of variables, and then you do some differential equations magic, and you arrive at this equation right here. And basically, the radial part is described by this equation. The uh, the part from like 0 to like pi, it's called like the zenith angle. It's that is described by something called a Legendre polynomial. And then the phi part, which is like the azimuth part, which is like the circle part in the rate in the spherical coordinates, that's described by constant times exponential square root of -1 m phi. I have no clue why Chihui would ask something like this, but I guess he did last year. Anyway, the quantum numbers, so n is principal, and it describes the size and energy level of the atom. L is the angular azimuth, and that describes the orbital shape. M is magnetic, and that kind of describes the orientation. And then spin is upspin or downspin, and like Pauli exclusion principle, right? And then I guess like the more relevant information from more specifically like last exam. So the function for when n is 1 and then L and M are both 0. First hydrogen slide, yes, I can. Last slide. Yeah, so is there a question? You guys probably will not be tested on Legendre polynomials and actually solving this equation. I think the main point is just to get you guys to see the radial equation, because on last year's exam, there was a question where you basically disregard the phi part and the theta part. So you disregard the Legendre polynomial, you disregard the exponential term, and you just look at the radial term. I believe it's a question where it's like you find the probability curve or something, or the distribution function of the atom when like n is equal to 1, m and l equal to 0, and then like n is equal to 2, and then l and m are equal to 0. So yeah, this is when n is equal to 1, m and l are equal to 0. That's the equation that pops out. So a naught is just a constant called the Bohr's radius. We just take a bunch of junk and we substitute in a naught, which is 0.529 angstroms. So basically, if you go back to the first slide, that's basically here. So basically, you have R over N times A naughts. So you substitute all this junk out for A naught. This is a normalization constant. And yeah, so like on last exam, like that would have been your answer for the hydrogen question. Yeah, and then the energy levels for hydrogen, as N increases, it like increases by a factor of 1 over N squared. And then this is just a table of allowed states for hydrogen atom in the first 3 shells. Are there any questions about this?
Let us know if there's any part you want us to like repeat as well, if you like didn't catch it.
Is there an intuitive reason for why the energy is negative?
Oh yes. So basically, so because of the photoelectric effect from back like on one of the previous slides, so basically to eject an electron from an atom, right? To kick an electron out of an atom, you shine a light on it, and then the light has to have a certain amount of energy before the electron gets kicked out, right? And so that's kind of a remnant from the photoelectric effect, so that like you have negative energy, and then once you go to a certain amount, like it gets more positive and requires less energy from the light to kick the electron out. if that makes sense. Does that answer your question?
Yeah, that answers.
Okay. Yeah. Yeah, and then the Kronig-Penney model. So the main reason why I'm showing you this is just to convince you that the band gap theory for semiconductors is valid. So basically what you can do is you can model each atom as a crystal in a potential well. So the atoms will reside in like region 1 here in the well. And there's a periodic boundary condition. So you just like the crystal, you copy and paste these potential wells, right? And basically, like before, this is your energy level function for the hydrogen. So like something like this. And then basically when you have it in a crystal, it looks something more like this in the bottom figure 3.5. And then so basically atoms reside in region 1, and then there's a potential barrier due to electric field in region 2. And then you use periodic boundary conditions between 1 and 2 and Schrodinger equation to solve. In this case, it's time dependent, Schrodinger. Do the electrons exist in region 1 or 2? So basically the entire atom only exists in region 1. Region 2, for simplification, we will say that the particles cannot exist in region 2. So we are assuming that each potential well is an infinite potential well. Yeah. You can probably get a more precise description of this elsewhere, but I think infinite potential well also works for this derivation. So basically, we're not going to go through the full derivation, but basically some basic steps. So it's in Neamen 3.1. So you go through Bloch's theorem, which states that every wave function is in some form, some function u of x times e to the j kx. And then you plug this into the time-dependent Schrodinger equation once for each region. Wait, actually I lied. The electron can exist for region 2. Otherwise you don't get the solution here. Yeah. Okay, yeah, I was wrong before because the electron can exist in region 2 because of like bonding, and the electric potential isn't going to be infinite. Sorry about my lying. So basically for region 1, you solve the time-dependent Schrodinger equation. And then for region 2, you also solve the time-dependent Schrodinger equation. And then you obtain a solution, and you plug in the boundary conditions. And then you get a system of 4 equations with 4 unknowns. And then you solve a system of equations by a determinant. You do a bunch of other stuff. But basically the result you get is that on the left-hand side, you have a function that is a linear combination of a sinc plus a cosine. And on the right-hand side, you get another cosine. And then basically what happens is you see here in C, so because the right-hand side, it can only have a value between 0 and 1. So we cut off the value between like +1 and -1 on the y-axis. And then that kind of forms our allowed values in our E versus K diagram. And then we can form our reduced K space, which is a conduction band and a valence band, right? In figure 3.11.
Yeah, so this reduced K space is also called the Brion zone, where it's kind of like since the energy states are periodic as you move out with respect to K, you can just say that, all right, we're going to look at this one reduced space and do all our work here, because whatever happens here will be replicated in other K spaces.
Yep. Are there any questions about this? How are you guys doing? Are you guys confused or?
Yeah, I know there's a lot to go over.
Yeah, this class is a handful.
All right, if not, we can go to the next slide.
You guys want to take a break or?
Do you guys want to keep going? The next stuff is all like semiconductor stuff.
Yeah.
All right,
right.
fuck it, let's go.
Let's go. So you have group and phase velocity. So basically you have like wave packets, right? So because of uncertainty principle, you can't know position and momentum at the same time. So what happens is you get a bunch of like waves with different momentum, and you get a wave packet. And basically the wave packet, it looks something like this. And the wave function phase, it moves with phase velocity omega over k. And the group velocity, so the group velocity is kind of the speed, the velocity of the entire like packet. And then the phase velocity is just the velocity of the inside thing, which in the phase is omega over k, and then the group, so basically the velocity of the entire like envelope is the derivative of omega with respect to k. And also this is how your radio transmits like information. It uses amplitude modulation. So it basically adds a high frequency signal with a low frequency signal. And then the high frequency signal, what it does is that's how it transmits from your radio to the station, or the station to the radio. And then the low frequency signal is that's your actual like music. So I thought that was kind of cool. Are there any questions about this?
All right, on to the next slide.
So the next topic is just the motion of electrons and holes. So basically when an electron gets excited, so at 0 degrees Kelvin, so when everything's like frozen, all the electrons in the semiconductor is in the valence band, and the semiconductor becomes basically an insulator. It cannot, the electrons cannot move. But if it gets warmer, let's say around like room temperature or 300 Kelvin, the electron gets excited and the material becomes conductive and the electrons can move. And so when the electron gets excited to the conduction band, it also generates a hole, which is the absence of an electron. And when an electric field is applied, the electron and holes move. And the effective mass is something that arises due to internal forces in the semiconductor material. Yes, we will post this after. We will be uploading this video to our YouTube channel. So yeah. Anyway, as I was saying, effective mass. So basically, if you have like Newton's law, right, you have the sum of all the forces is equal to m times a, right? And the sum of forces is external forces, so forces outside, plus internal forces, so forces inside. And so what we do is, because we can't always look at the internal forces, is what we do is we take out the internal force and we account for this by the effective mass. And another way to see effective mass is that if you look at the equation of motion for an electron and electric field, so basically the equation that tells you how it moves in an electric field. So you have force, or the time derivative of momentum, is equal to E times the charge times the electric field, right? And then from de Broglie's relation of momentum is h bar times k, we get that the time derivative of k is equal to negative E times electric field over h bar. And also we get from the traditional relation, m dv dt is equal to negative E times electric field over h bar. So how can we find dv over dt? What we do is we take dv over dt is equal to 1 over h bar time derivative of dE with respect to k. So we know that E is equal to h omega, and then we know that so we know that V is equal to lambda times F, right? From just basic wave equations. And then what we can do is you can say that because k is equal to 2 pi over lambda, and then omega is 2 pi f, what we can do is we can take omega over k, and that's our V. And you basically do a bunch of like algebraic manipulations like that. And then you get dv over dt is equal to 1 over h bar time derivative of dE over dk. And then you do some calculus. So here, like, you do the chain rule. So you have dE over dt. So because E is also dependent on k, you have dE dt is equal to dE dk times dk dt. And you keep going. And you eventually arrive at the equation for effective mass, which states that effective mass is equal to h bar squared over the second derivative of energy with respect to k. And yeah, are there any questions about this?
All right, next slide.
Oh yeah, and then a trick to think about second derivatives. If your function is concave, it's negative, and if it's convex, it's positive. It might be helpful for future things. So what is a hole? Repeat after me. A hole is not a proton. So a hole is just the absence of an electron in an atom, and this allows the atom to exhibit properties of a positive charge. So when a hole is created when an electron gets excited to the conduction band, but destroyed when the electron comes back down, hence the term electron-hole pair. And then and then you can introduce holes into semiconductor through doping. So if you replace like an Si atom in a crystal with a group 3 element like boron, so you can kind of see the hole moving through a semiconductor, almost as if it were just a normal positive charge. But the reason why it can behave like this is because the atom is positively charged without the electron being there. And so it transferring that electron vacancy is just almost behaves practically like a positive charge. Are there any questions about holes? Are you guys good? All right. So drift current is the next thing. So whenever you hear about like drift current in ECU2, it refers to current due to applied electric field. And basically you add the whole electron current to get the total drift current. So basically it kind of makes sense, right? So you add the current due to all the positive charges plus the current due to all the negative charges to get the total current. So some helpful equations to get the total drift current. So just listed here. So carrier mobility is a parameter that just defines how easy a carrier, so an electron or hole, is made to move. So it's dependent on effective mass, average scattering time, which is the average time for collision, and then the charge is the constant that's there, because we're talking about electrons and holes. The charge conductivity is just how susceptible the material is to current, and that's dependent on the number of holes or electrons that are there, and then the charge carrier mobility. And then the average drift velocity is just the average speed at which the electrons or holes go at, and that's just equal to the electric field times the carrier mobility. And then you have the total conductivity, which is just the sum of the hole conductivity plus the electron conductivity. And then the current density is just the total conductivity times the electric field. Or you can also find this by charge time so basically you use this equation up here. So you get charge density is equal to like charge times the number of holes times the average drift velocity minus the number of electrons times the average electron velocity. You guys have any questions about this?
Quick note about the mobility. I know we give an equation for it, but in practice, it's not exactly an easy thing to calculate. So it would probably be helpful for you guys to like look up what the mobilities are at room temperature for like silicon and germanium. Because like effective mass is an easy thing to calculate as well. So usually like people just get the mobility experimentally, and then they like plot a graph of it based on temperature. So it might be helpful for you guys to like look up what the mobilities are.
Instead of calculating the second derivative of energy with respect to Okay. All right, Ravi.
All right. Yeah, now we get to the semiconductor stuff. So one way people measure how many electrons and holes they have in the conduction band or the valence band is through the Fermi-Dirac distribution, where you have essentially these two curves here, like two curves. Like here you can see EC, which curves towards the right, and then you'll have another one which isn't shown in this graph, but it's EV, which is essentially a negative version of this, where it's like square root of EV minus E. And that basically says, and when you take the integral of your Fermi-Dirac distribution equation versus the multiplied by the density of states equation, you get the area underneath where those two graphs intersect essentially tells you how many particles are in that are in that band or in that region. So the as you can see, the Fermi Dirac distribution is dependent on both energy level as well as temperature. So if we actually if you actually like increase the temperature of your element or of your crystal, the Fe graph would slowly start to flatten out. If you look at where the arrow is pointing, like EF, that's your Fermi level, which is one. We'll show the equation for that later, but that's essentially kind of like your middle point of the Fermi Dirac distribution, and you can use that to say how many carriers are on the conduction band versus the valence band. And as you increase temperature, this blue graph slowly starts to flatten out and become more horizontal, which means that more particles enter the conduction band. Or this one specifically is for electrons. And then if you wanted to measure holes, you would take the same integral, but instead of Fe, you would do 1 minus Fe, which would mean that this blue graph would be flipped over the y-axis.
Mm-hmm. Oh,
yeah.
So basically, so you semiconductor versus metal versus insulator. So you know the difference between an insulator and a semiconductor is because between an insulator and a semiconductor, the insulator has a very, very large band gap. And so it's very unlikely that something from the valence band will get excited up to the conduction band. And for the semiconductor, there's a much lower band gap, meaning that it's easier for something in the valence band to get excited up to the conduction band. In the metal, there's practically no band gap. The valence and conduction band are practically on top of each other. And like they can basically move freely between each other. So one interesting note is that for a semiconductor, there are an even number of valence electrons per atom, while for a metal, there are an odd number of valence electrons. So in the so like why is this?
Does anyone have an idea? If you think about like the transition metals in the periodic table and about how they like collect valence electrons, that might be a clue.
You can think back to the exercise we did when there was like when we did like the current density exercise, where we mentioned like bubbles rise up and then the marbles roll down. So like what would happen if, let's say, there were an even number of, or actually first, what if there were an odd number of electrons in the valence band? What would the current be? Would it be 0 or non-zero?
Or another question could be how many electrons can you fit in a valence shell? Assuming that it's not the first shell. Anyone? Yeah, it's 8. It's actually 8 for all elements. But as you can see, if you notice, 8's an even number. But all these metals have an odd number of valence electrons. So does that tell you guys anything? Anyone? Right. So usually when people talk about metals, they refer to the transition metals. So like that huge region in between column 2 and column 3, and that group collects valence electrons differently than the other groups.
Oh, by valence electrons, I mean like electrons in its valence band. Sorry if that was ambiguous, but
Yeah. Yeah, that's correct.
Yep.
If you have an even number of valence electrons, the outer shell has the possibility to bond with other atoms and create like an overall neutral shell and fill up the 8 valence spots. But if there's an odd number of electrons in the valence band, so if there's like an odd number of valence electrons, or you can kind of think of like the valence band as like the electrons close to the all right, we're gonna get to a little bit of a solid state physics here, but when you have like a particle, or like you have an atom and you fill up its valence shell, its valence spots, you have a neutral atom. But then when you excite it, the electron becomes a free electron. So it's not under the influence of the atom that it was once a part of, and it's free to roam around. So when these metals with an odd number of valence electrons start to coalesce into a lattice structure, they're not able to find a home for these odd electrons, and so they kind of like float around these atoms, and they don't really have like a home or like a shell to like bond with, and that essentially creates a conduction band, because you just have a bunch of like free electrons. And I don't know if you guys have learned this in previous physics classes, where like metals you can think of them as like a sea of electrons. This is where that sea comes from, because they have an odd number of valence electrons that aren't really able to fill up the shells. And so because of that, metals actually have electrons in the conduction band at 0 Kelvin, whereas semiconductors and resistors do not.
Mm-hmm.
And that brings rise to like superconductivity and all that good stuff. But this is the core concept behind that.
Yep. Yeah, and that's why semiconductors act like insulators at 0 Kelvin.
Yeah.
Yeah.
You can think of a semiconductor as kind of like a resistor with a really small band gap.
Yep.
So, and because of that, we're able to take advantage of it.
Mm-hmm. Yeah. You can also think of like the marble rolling down a hill. So if there's an even number, there's always going to be an electron that will cancel another electron out. But if there's an odd number, there's going to be one odd electron out that can't be canceled. And so that will roll down the hill somehow.
Yep, exactly.
Yep. Okay. So density of states. Yeah, this one. Yeah, hopefully this one isn't too dense. So it's basically the number of states available in a unit of volume per unit energy. So basically, step one, you think of, what states are allowed. So let's say we have like a sphere of radius k, and we take some sphere of radius k with energy E, and we divide it by L, right? So we get states per volume at some energy E, right? And then we take the derivative of this function with respect to E. And that will give us the density of states. if that makes sense. So basically you get, you know, so you get the K's divided by the volume, and then you take the derivative with respect to energy. So you take the change with respect to the change in energy. So yeah. So you see from the graphic, calculate density of states per unit energy per unit volume, i.e., if we have a constant energy sphere E and we increase it by dE, how many additional states will we have added? That's kind of the idea behind it. Yeah. So for 3D, if we were to use it as an example, so we have, so for each K state, so each K is equal to N times 2 pi over L. And that just comes from, like if we have, so there's two ways to do it. One is if you have assume a crystal lattice or a infinite quantum well. So if you assume a lattice of length L, then you get K is equal to, in each direction, K is equal to N times 2 pi over L. So, and then you cube that. Because basically the 2 pi over L comes from the fact that the crystal is periodic, and then it's of length L. So one state over 2 pi over L cubed times the spin, because you get upspin and downspin per K space, to get the density. And then you get the number of states inside a sphere of radius K. So you want to multiply that by the volume of the sphere. So 4 pi cubed, 4 over 3 pi K cubed. So basically the value I gave before is just like the number of states within this one box, right? So if I, this one box of length 2 pi over L, or this cube, yeah. So you take that and then you multiply it by 4 over 3 pi K cubed. And then you get the number of states inside the sphere. And then what you want to do is you want to take that, divide it by the volume of the box that you have, so 1 over L cubed. And then you take the derivative with respect to energy to get the density of states per unit energy per unit volume. Any questions? All right, moving on. Do you guys want to do these exercises, or do you guys want to do some intrinsic and extrinsic semiconductor stuff? Because we have 22 minutes left. Okay. So in thermal equilibrium in a semiconductor, the number of electrons is given by this equation where N is NC is the number of states in the conduction, and V is the number of states in the valence, the density of states in the
Yeah,
valence.
so
Yeah.
NC and NV are like the effective density of states. So when you like plug in all the equations and then get something out of it, you can plug in those constants, and you can actually look those up for silicon and germanium. I think it's something like 4.4 times 10 to the 17 for NC in gallium arsenide, and 8.9 times 10 to the 18 for NV in gallium arsenide as well. Yeah, these are all like constants you can look up, find out online easily. And yeah, so you use those, and then you find the difference in energy between the conduction band and the Fermi level, divided by KT, K being your Boltzmann constant, and that's how you find out how many electrons are in your conduction band, and you can similarly find out how many holes are in your valence band using a similar equation.
Yeah.
Yeah.
EF minus EV is the difference between Fermi energy. Which constants are temperature dependent?
Technically, all of them are temperature dependent, since as you excite a crystal, it starts to like, the atoms at each corner of the lattice start to like move more and more, and that creates more energy states. So actually, Cody, do you want to go back to the density states equation? Or, yeah. So if you look at this like sphere, when we relate an energy to K space in a graph or something, the K is actually like momentum. So as you like move farther and farther away from the origin, that's like kind of dictating like the amount of momentum a particle has. And like according to the Pauli exclusion principle, you inside like a crystal, no two particles can be at the same state. And state being like they have the same momentum, same location, same position, same spin, all that good stuff. So no two particles can be exactly alike. And so like as you go further and further out of the this graph, the density of states essentially says how many particles you have with this much momentum and this much energy, or like, yeah. Yeah, so then when you go back to the, yeah, so like NC and NV are both temperature dependent. N naught, P naught, which is like your number of electrons and number of holes at thermal equilibrium, they're all temperature dependent. But usually you can assume that it's 300 K, which is room temperature, and then you can just look up those constants.
Yeah, if I recall correctly, NC and NV depend on temperature by a factor of T to the 3/2. But you can double check me on that. You can probably find that equation online. Yeah, and then EF minus EV is the difference between the Fermi energy level and the valence energy. And then EC minus EF is the difference between the conduction level and the Fermi level.
Okay, yeah, so all semiconductors have three modes or three regions that they act in. So if we look at this graph here, and if you look at the X and Y, this is actually like a 1/T graph, which means that the further right you go, or like the larger the X becomes, the lower in temperature you actually have. So yeah, if we look at C, we'll start at 0 Kelvin, where the semiconductor is in freeze out mode, where we talked earlier, there are no electrons in the conduction band, everything's in the valence band, no conduction is happening. It's essentially a resistor. But that quickly changes as you increase the temperature up even like a smidgen to like a couple Kelvin. And then you start to enter the extrinsic region, which is where the number of carriers in your conduction band is determined by the amount of doping that you have. So let's say you dope it with like, you dope your silicon crystal with like phosphorus. Phosphorus has 5 valence electrons, silicon has 4. That extra odd electron gets to go to the conduction band. And so your N naught becomes equal to the, it becomes dependent on how much you dope your crystal with. And then that's usually where you want to keep your semiconductors in. You want to keep them in this extrinsic region, because afterwards, when things get too hot, usually around like 700 Kelvin, you start to see this like dip up into the A region, which is the intrinsic region, where your number of electron pairs in the conduction band equal the number of hole pairs in the valence band. Yeah, so we'll first talk about like intrinsic semiconductors. So intrinsic means pure, like no doping, like what you see is what you get. Like if we're talking about silicon, it's just silicon. If we're talking about gallium arsenide, there's nothing else there. So any holes or any electron hole pairs that you create are equal. So like if there are 2 electrons in the conduction band, there are 2 holes in the valence band. And so that's like a pretty useful relation. And this relation, N naught P naught is equal to Ni squared. That holds no matter what your state is, whether it's extrinsic, intrinsic, or freeze out. And so Ni is your like it's like your intrinsic number of intrinsic carrier concentration, and that's calculated with this handy little formula. And so yeah, you can use this formula when you're in thermal equilibrium or in the intrinsic mode. And then you can calculate the Fermi level here. And you can notice that there's actually a temperature dependent part with the L at 1/2 kT ln. So this is basically saying that your Fermi level actually like can go up and down. It starts at the halfway point, but it actually can go up and down based on your temperature. So as your temperature increases, the Fermi level gets closer to the conduction band. Yeah. And so then extrinsic semiconductors, so like I said, like, so when you dope them, whatever you dope them with, that becomes the number of carriers that your crystal has. So let's say you dope your silicon with like 5 × 10⁻15 carriers per centimeter cubed. So that would mean that your N naught is approximately equal to 5 × 10⁻15. And so when you're doping, you usually want to dope your crystal with an element that has either 1 greater or 1 fewer electron, because it's like easier to control. And that's why we're able to say that your N naught is equal to the concentration that you doped with. And same with P naught, because you're only giving 1 extra, or you're a 1 extra electron or 1 extra hole. And so similarly, like, so when you dope them, when you give a crystal extra electrons, then there's an excess electron concentration, and your crystal is now N type. And then vice versa, if you dope your crystal with holes, then it becomes P type. And your Fermi level is like influenced heavily because of that. And here are the other equations for that down here. And you can see actually in the diagram here, this is for an N-type crystal. The phosphorus ions are donating their extra electrons. into the conduction band. Where so there's only one hole in the valence band, but there are 3 electrons in the conduction band because of the doping.
Yeah. You can also kind of think of this like, let's say if you have like a village with like, let's say 100 women and 100 men. So if you think of like holes in electrons as like women and men. So let's say you have like 100 available men that are available to date and 100 women that are available to date. And then you suddenly place a army camp of 1,000 available men.
And these men are like hot too. So
yeah. So you expect
So they-
them. You can go, Ravi.
oh yeah, so then like because there's like so much more men, the amount of like it's harder for men to find like a pair to pair up with. So then you get excess men who are left without women to comfort them. And in a sense you get excess electrons without any holes to pair with.
If you have an N type.
Yeah, and all this applies for P type as well.
Yeah. And then the NP product always applies, because if you increase like the amount of men by a factor of 10, then well, you kind of expect the amount of available women to also decrease by, you know, a factor of 10. So
Yeah. So if you're given an equation, or if you're given the ND, if you're given ND, like the number of donors for the ND stands for donors and the NA stands for like acceptors. So if you ever see that in your problem, that's what it implies. So if you're given like 5 times 10 to the 15 donors, you can say your N naught is equal to ND, and then your P naught is actually equal to Ni squared over N naught because of the NP relation. And that's how you find how many holes there are.
yep. So this is our last question for you guys. Yeah, you guys can take as long as you guys want, or if you guys have any questions about the material we went over previously, feel free to ask. But yeah.
Just like anything, even if it's unrelated to what we've gone over.
Also, you guys are really smart, so don't doubt yourself when you have an answer.
Yeah, this class is a lot, but it's like I feel like you guys will get it. Any final questions?
We'll email we'll email the professor and the TA these slides for them to distribute, and they'll be posted on